All right, let's dive into one of the biggest, most mind-bending ideas in all of computer science, the halting problem. Seriously, this thing touches on the absolute limits of what any computer or even any AI can ever do.
So if you've ever written a line of code, I'm sure you've been there. You hit run, you wait, and you just get that spinning cursor of doom. Nothing happens. You're stuck in an infinite loop. Well, it turns out that's not just some annoying bug. It's actually a clue to a deep, fundamental problem that's literally impossible to solve.
So just for a second, let's dream a little. Imagine we could create the ultimate debugging tool. Let's call it the HALT program. You could feed it any piece of code, no matter how complex, and it would spit out a perfect 100% accurate answer. Yep, this will finish. Or, nope, that one's going to run forever.
I mean, can you even picture it? A world with no frozen apps? No servers getting stuck in some recursive nightmare? It would be the holy grail for every developer on the planet. But here's the catch. The whole reason we're talking about this is because we know with absolute mathematical certainty that a program like that can never exist.
And the person who figured this all out? None other than the father of modern computing himself, Alan Turing. He's the one who gave us this absolutely ingenious proof that shows exactly why this dream tool is just impossible.
Yeah, way back in 1936, Turing proved that the halting problem is what's called undecidable. That's just a fancy way of saying no algorithm can ever be written to solve it for every possible case. And he did it with this beautiful little trick called a proof by contradiction. Okay, so stick with me here. This is where it gets fun. To prove halts can't exist, Turing's strategy was to assume for a moment that it did. And then he invented this other little troublemaker program. Let's call it Paradox. The entire job of Paradox is to be a contrarian. It's built to do the exact opposite of whatever our perfect halt program predicts.
So here's how it works. It's a bit of a head-scratcher, but the logic is so clever. First, Paradox takes some other program as its input. Then it uses our magical halt tool to ask, hey, will this program stop if I try to run it on itself? If halt comes back and says, yes, it will finish, well, Paradox immediately throws itself into an infinite loop. But if halt says no, that thing will loop forever, Paradox just stops right in its tracks. See, it's designed to make halt a liar.
And this is the killer question. This is the moment that breaks everything. What happens if we take the Paradox program and feed it its own source code as the input? What on earth would our perfect halt program predict then?
This is where the trap springs shut. Let's think it through. If our perfect halt program looks at Paradox running on itself and says, okay, it's going to halt, what happens? Well, Paradox's own rules say it must loop forever, so halt was wrong. Okay, what if halt predicts the opposite? What if it says, nope, Paradox is going to loop forever? Well, then Paradox's rules say it has to halt immediately. Halt is wrong again. It's a total contradiction.
You see, there's no way out. No matter what our supposedly perfect halt program says, it's proven to be incorrect. It's a paradox, and the only logical way to resolve a paradox like this is to realize that our initial assumption, the one that said a perfect halt program could exist in the first place, had to be wrong from the start. It's simply a logical impossibility.
So you might be thinking, okay, that's a neat little logic puzzle, but this isn't just some abstract idea. This theoretical limit has real, everyday consequences for pretty much anyone who writes software.
And that's what leads us to all the workarounds we use every day. Because we can't perfectly predict if something will stop, what do? We use timeouts in our build pipelines. We build watchdog systems that just reboot things if they seem stuck. And of course, we have the classic user-facing solution, the force quit button. These aren't elegant fixes, you know? There are clumsy but necessary ways of dealing with a fundamentally unsolvable problem.
And really, this points to a much bigger idea. The halting problem isn't just some weird quirk of programming. It's a fundamental boundary on what we can ever hope to figure out using computation.
I love this analogy. Think of it like those old maps of the world, where at the edges the map makers would just write, "Here be dragons." That's what the halting problem is for computer science. It's the line on the map beyond which our algorithms and our logic simply cannot go. It tells us that there are some truths about our own programs that are just unprovable.
And you know, Turing wasn't the only one exploring these boundaries. His work fits right in with other huge ideas, like Gödel's incompleteness theorems in math. They're all part of this fascinating field called computability theory, which is basically the formal study of what computers can and, more importantly, cannot solve.
Okay, but let's bring it back home.
Why does any of this really matter to you and me? Where do we actually see this theoretical problem pop up in the wild, in the tech we use every single day?
Well, it's everywhere once you start looking for it. You know when your computer can't tell if a program has crashed or if it's just really busy? Yep, that's the halting problem in action. Or when your code compiler can catch a simple infinite loop but totally misses a more complicated one. That's it too. And hey, even the most sophisticated AI models writing code today, they are bound by the exact same limitation. They can't perfectly predict their own code either.
But honestly, knowing about this isn't a downer. In fact, it's the opposite. It's empowering. Once you understand what's truly impossible, you can stop chasing perfect solutions and start focusing on what really matters. Building smarter, safer, and more resilient systems that can handle the messy reality of the world. It makes us better engineers.
There's this wonderful sentiment that Turing and others in his field really understood. It's this idea that there's a kind of beauty in what we cannot compute. It's a humbling and I think kind of profound reminder that even our most powerful tools have their limits.
So, the next time you're sitting there staring at that spinning cursor, getting frustrated with a program that just won't stop, maybe just take a second. You haven't just stumbled upon a simple bug. You've actually brushed up against one of the deepest and most fundamental truths in all of computer science.